Okay. I thought it already stared it, just in case.
We can see G9B antennas and feed lines on the screen.
Okay. Unfortunately, I'm not.
Oh, that's not good.
Where did it go? System sharing, I'm recording. Stop this there. There we go. All right. Here's some typical antennas. Uh, Over on the right is a uh, vertical. Looks like a quarter wave vertical. This one in the middle on the bottom is a magnetic. Well, I take it back. Some kind of loop, I'm not sure. Um, One up at the top is another kind of loop antenna where these are spirals, and one is used as a driven element, and the other one's a reflector. So it makes it directional. It drives the beam uh, forward. This one down here in the bottom left is called a J-pole. A lot of people build their own, just make it out of copper pipe, regular plumbing fittings. They're very easy to make. And this is some form of Yagi up here. Might be a uh, dual band. So we're going to talk about random wire antennas, dipoles, and verticals, basically. So a random wire antenna is just that. It's a random piece of wire that you make as long as you can, preferably at least one wavelength. The longer, the better. It gives it what we call a bigger aperture, so it receives more signal. You attach one end to a tree, a pole, something, keep it off the ground. Although there's this Russian girl that does a lot of uh, blogs on radio stuff. She's an amateur, and she has buried antennas and showed that they work just as well as when they're up in the air.
Wow.
Um, the other end of it gets connected directly to your antenna tuner or your transceiver. So it's more than likely coming into your shack. That means it's bringing in any kind of radiated power, reflections, or whatever pickup. So you could wind up with having uh, enough RFI that it's on the cabinets of your equipment, things like that. You could get on an RF burn. So typically, these are only used for low power type operations, maybe QRP or something like that. Can't say I've ever tried one. This is going to be the most common, and it's probably the basic component of most antennas, called a half wave dipole because the elements are a half wave long. Each element is a quarter wave, so they add up to a quarter wavelength. It'll be right around 72 ohms uh, feed impedance. And like I said, most other antennas are some variation of this. Even if it's a vertical, um, it's usually just one half vertical and the other half may be in radials at 90 degrees. So it's only radiating out of uh, one of the elements, which is why it doesn't have as much gain as the dipole. And it's also why it looks like 35 ohms instead of 72, because it's really half of the antenna. Uh, if you're going to do an antenna, uh, you need to know how to calculate the length of the elements. So when you pick particular frequency you want to operate at, um, you need to use the formula that we talked about early on, where lambda, or the wavelength, is equal to the speed of light divided by the frequency. Now you notice this top formula also has this 0.95, and that's approximately the velocity factor of the speed of light when it's going through a conductor, like an antenna element. So if we include that in the formula, and we also stick in the 39.4, it's really 0.37, and divide it by 12, because that gives you inches, and dividing by 12 will give us feet. Um, then if we use the result, it's 468 divided by the frequency in megahertz, and they'll tell you how long a half-wave dipole needs to be in feet.
Question.
Okay.
I have no idea what that symbol means. It's your length of formula equals, what is that? I've never seen that before.
Oh, the approximation sign, the little wiggle.
The little thing in front of the equal sign, yeah. What is that? It's not an X. It's like an upside down Y.
Oh,
Lambda.
lambda. Lambda, we use lambda to represent wavelength.
Okay.
It's a Greek symbol.
Okay.
It's used in sororities and fraternities.
Yeah. No, don't know that. Didn't go to college, sorry.
Okay.
All right.
So
So that's wavelength, as you said?
wavelength.
Wavelength. Okay.
How far a wave, one cycle of a wave travels, okay,
Okay.
to complete a cycle. It takes, it's if it's going at the speed of light and you divide the frequency, then it's going to tell you how many, if you're using 300 million meters per second, it'll tell you how many meters long that wave is from start to finish for one cycle. That's
All
how
right.
far it
So,
that's how far it travels.
all right. So I wrote down the formula, but can we actually do one at some point
Yeah,
so that I
yeah.
understand how to?
So
Um,
this is just to simplify it, to go directly from a half wave antenna to feet. So you just need to remember the 468. So this example, say we wanted to do it for the 40-meter band and do it at 7.15, which is in the voice band. So we're doing single sideband. It would say that that dipole needs to be 65.5 feet long. It'll probably wind up being a little shorter than that because whatever you calculate, you're going to have to change if you actually build that antenna. It never comes out because velocity factor might be different. Other things around are affecting it. So the old thing with antennas is everything affects everything. So we talked a little bit about feed point impedance of uh, the half-wave dipole and the vertical. So the half-wave dipole is normally 72 ohms, either in free space or high enough above the ground. So if we were to feed it with a 50 ohm coax, we're going to have a 1.5 to 1 SWR. If we fed it with 75 ohms, we're going to have a really good SWR, be 1.04 to 1. If we start to feed the antenna someplace besides the middle, let's call it off center. Typically, an off center would be uh, like 2080 or 2575, maybe 3367, some ratio like that. And now that feed point impedance is going to look more like 200 to 300 ohms.
And why would you do it off center? What would be the benefit of that?
Well, it turns out that if you feed it off center, you can get more than one band. If you
I
feed
was
it in the
wondering.
center, uh, we're going to be optimized around well, we did it for 7.15 and a fairly narrow band. You may not get the entire 40-meter band.
Okay. So
If I if I
because
feed it
the length obviously gives you the different frequencies you can go on. So if you have one long one and one short one, that's two different frequencies.
right, well, fed in the center, the half-wave dipole is going to be resonant at one frequency.
Right, right.
If I
But
feed it off center,
mhm,
it'll be resonant at more than one frequency.
that's what I was wondering. Okay,
If
yeah.
I do it just right, I can make the resonant points line up with the 40-meter band and the 20-meter band and maybe the 10.
That's what I was wondering because I know when we were working on the dipole for field day, it had to be exact to get to where he wanted it. So I was wondering if that was how you could do that.
Yeah, and you wind up taking the ends and usually folding them back on themselves a little bit to shorten it, and then you
Mm-hmm.
test it, and then you might do another one. So
Okay.
you've gone too far, and you try to get it as close as you can.
Okay.
And you have to do both ends the same,
Okay.
because if you don't, you're going to have an unbalance, so you're going to have common mode coming back down the feed line.
So has anybody developed one of these dipoles that you can automatically adjust from like in your shack where it's moving? The ballon is moving. Has anybody done that successfully?
Not that I'm aware of.
Okay.
Now, you can do a similar thing with a mobile antenna called a screwdriver, where it actually has a motor
Huh.
Uh-huh.
and it changes the inductance on the base coil, so you can tune it for pretty much the entire amateur radio band, HF
Hmm.
band. Okay, now if we move all the way to the end, we call that an end fed, and the impedance is going to go up to like 3 to 5,000 ohms. That's why you normally would use a matching transformer to get the 50 ohms up to 5,000. So you'd need something like a 50 to 1, or not a 50 to 1. 100-to-1 ratio to get up that high, although usually because of other losses, they're closer to 300, 3,000. So typically for an end-fed, the transformer may have several taps, usually at 49, 56, or 64-to-1. And one of those usually works pretty well. The end-fed half wave gives you more resonant points, but again, you got to adjust the uh, transformer turns, and a lot of times you have to put a little capacitor across the input uh, to adjust it, to tweak it, and also change the length of it a little bit. So it's a little harder to get it tuned up to get all the band or most of the bands, and it'll cover most of the bands if you got it right.
Okay.
Main thing to remember as you go from the center towards the end, the impedance increases. Doesn't matter which end you go to. And usually on the case of an end-fed, you're tossing it up in a tree. So, one end is down at your ground, at your radio, and the other end is up in a tree, over a tree. Okay. Polarization is another factor with an antenna. And vertical antennas are what we call vertically polarized. And one of the things about a vertical antenna, because it's really half of a dipole sticking up, and the other half is virtually in the ground or radials on the ground, that other virtual half of the antenna is being absorbed in the ground. So it has any energy that went to that half of the antenna is being absorbed. So it's high loss. In the case of a horizontal antenna, like a horizontal dipole, it's horizontally polarized, and those ground waves that are produced are being reflected off of the ground. So it has a lot less ground wave loss, which is another reason why it typically has higher gain than a vertical. Now, when we say they're polarized, if you look at the current, the way the current flows along the conductor of the antenna, if it's going back and forth horizontal with respect to the earth, we call that horizontally polarized. If it's traveling back and forth vertically with respect to the earth, we call that vertically polarized. Okay. Each antenna is going to have a different radiation pattern, and it will be affected by stuff that's around it, how high it is, what it's located by, and the basics of the antenna itself. So a half-wave dipole, if it was in free space, we say it's not close to the Earth, you could put one up in space. The radiation pattern is going to look like a figure 8, like this bottom azimuth pattern down in the bottom left. They call that a figure 8 pattern. It's got 2 lobes. If we looked at it vertically, we'd see those 2 lobes with a little bit of elevation on them because of some ground effect. As long as that dipole is at least a half a wavelength, or lambda over 2, height from the Earth, you're going to have a very similar pattern. It's not going to change much as you from what it would be at free space. If you lower it and you get it down close to the ground, like a tenth of a wavelength or eighth of a wavelength, you get this more omnidirectional pattern. It tends to be a higher lobe uh, and kind of like an ellipse. It's almost round. So we call that essentially omnidirectional. And most of the power is up very high incident angles. So we can use a dipole antenna close to the ground for what we call INVIS, near vertical incident radiation, which allows you to reflect off of the ionosphere and come back down at a very short hop. So you might be able to communicate with somebody that's in the same county. Normally, with a dipole up at least a half a wavelength, you're going to skip right over them. You might get a long distance contact, but you're very unlikely to get a very short distance contact. Uh, we talked about the dipole impedance being about 72 ohms. Sometimes they say it's 73 ohms. It varies a little bit. Um, and it will have some reactance, which is what the J42 and a half is. Um, as you lower the antenna, not only does it change the radiation pattern, it changes the impedance, and the impedance decreases. So as you lower it enough, you can get it to look like 50 ohms, but it'll have a more omnidirectional pattern. It'll be much higher takeoff angle. And like we said on the other one, as you move the feed point towards the ends, either off center or in fed, it increases the impedance. So a couple ways you can either increase or decrease the impedance of the antenna by playing with the height or where you feed it. You can also lower the elements and make it inverted V and get it to 50 ohms.
But if you're bringing it closer to the ground, aren't you increasing the radiation? Or no?
Power wise, I don't know, but you are going to have most of your power is going to be at a high elevation angle.
Okay.
Which allows you to do a short skip. If I have a quarter wave vertical, basically half of the dipole, one of the advantages is it has a very small footprint where we calculated the couple slides back, a 40-meter half-wave dipole is 65 feet long. So you got to have space for a 65-foot antenna. If I do a vertical antenna for 40 meters, takes up a few square feet. Its radiation pattern is going to be omnidirectional, or a circle around the antenna, like we see in this azimuth plot. And it will have a null basically in the vertical axis. So you have these two lobes, kind of like part of a torus, a torus, or a donut around it, slightly distorted. So in the case of calculating the length for this half-wave antenna, we can do lambda over 4 is going to be equal to 234 divided by the frequency, and you get the length in feet. If you notice, all we did was divide by 2. So instead of 468, we used 234. Okay. If it's a ground plane vertical, what would normally have been the other element of the dipole, we spread out horizontally, either on the ground or bury it. We call those radials. And what that's doing is creating a big um, reflecting surface for part of the signal from the vertical portion of the antenna. And there's all kinds of stuff about whether those should be the same length and be resonant and all that stuff. Well, technically, they don't. They just need to be enough of them to provide a good reflective surface. Uh, Sometimes people will use like chicken wire and bury it under the under the sod, and it makes a very good radial system.
It might be good for HOA.
Yeah. Well, of course, you still have to hide your vertical, but
Well, there's a tree for that. There's a tree for that. Yeah.
okay. You can do a flagpole,
Yeah. Yeah.
and they sell them, and you can put a flag on it, and it's actually an antenna, a vertical antenna. Um, like I said, the radials are going to be horizontal or perpendicular, so they're not going to radiate, and uh, that lowers the feed point impedance. Whereas if we actually did a half wave dipole vertically, and we had both elements, we fed it in the center, it would still be around 72, 73 ohms. But it's kind of hard to do that, especially for any length. So, like I said before, sloping the radials, I can, in the case of a vertical antenna that's mounted above the ground, a lot of those will have radials as part of the antenna uh, that stick out around the base of that first element. And if you slope those about 45 degrees, it will change the impedance to right around 50 ohms. So you can make a good match to that. Okay, we talked about random wire, which basically the thing to remember is because it's that really long wire coming directly to your radio, you could have some significant RF current. For the quarter wave ground plane, sloping the radials at 45 degrees will get you close to 50 ohms. It'll have an omnidirectional pattern in azimuth. And you can calculate the length by either taking the half wave dipole formula and dividing it by 2 or using the 234 number, which is the same thing. And if it's a ground mounted vertical, then we have radials either on the ground or buried. Doesn't matter how far you bury them. And usually people will put them under the sod or get one of those sort of, they have a tool, kind of like a trencher that just makes slits, and you run it and then you can just kind of poke the wire down in those slits in the ground. The half-wave dipole has a figure-8 radiation pattern. If it's at least a half a wavelength high, if it's less than a half a wavelength, it becomes more of an omnidirectional antenna with a high takeoff angle. The impedance will be about 72, 73 ohms. It decreases as you lower the antenna. It increases as you move the feed point towards the end. Same formula, the 468 divided by the frequency to find out how long it is in feet. And it'll be horizontally polarized and have lower ground reflection than an equivalent vertical antenna would. So, what's a characteristic of a random wire HF antenna connected directly to the transmitter?
Charlie? Characters? Random wire. Oh, okay, wait.
What was the main thing we talked about on the random wire? About it coming into your
Oh
shack.
no, this whole chapter to me was totally confusing. I didn't follow much of it.
Oh,
Okay.
it can have a significant RF current coming into your equipment. That's one of the reasons why it's not very common.
Okay.
You might use it in a portable operation outside for, low power. Which of the following is a common way to adjust the feed point impedance of a quarter wave ground plane vertical antenna to be approximately 50 ohms?
Sloping your radials. I'm guess it was 45 degrees, so I don't know if that's downward or I'm guessing downward.
Downward. Yeah. Which of the following best describes the radiation pattern of a quarter wave ground plane vertical?
D, delta?
Delta.
Yeah. Sorry, my audio is off.
What is the radiation pattern of a dipole antenna in free space in a plane containing the conductor?
So it's a figure eight and it's right angles. So alpha.
Alpha, yeah.
How does an antenna height affect the azimuthal radiation pattern of a horizontal dipole HF antenna at elevation angles higher than about 45 degrees?
Charlie.
Yeah. Charlie, not Delta. Yeah. Okay.
Where should the radio wires of the ground mounted vertical antenna system be placed?
Charlie.
Yeah, Charlie.
How does the
Seven.
feed point impedance of a horizontal half wave dipole antenna change as the antenna height is reduced to 1/10 wavelength above the ground?
Feed point impedance decreases as you go above. So it's alpha or
Alpha?
Baker, Bravo, sorry.
Okay, so let me read it again. How does the feed point impedance of a horizontal? Yeah, Bravo.
It goes down.
It goes down, yeah.
How does the feed point impedance of a half wave dipole antenna change as the feed point is moved from the center towards the ends?
It
Alpha.
goes up. So it's
Alpha.
Which of the following is an advantage of a horizontally polarized as compared to a vertically polarized HF antenna?
Vantage.
it's lower ground reflection.
Reflection,
Alpha.
right.
Right. What is the approximate length for a half wave dipole antenna cut for 14.250
Well,
megahertz?
here we go. This is where I just don't hold on, let me see if I can
Okay.
figure it
Remember,
out.
468 divided by the frequency.
Oh my gosh. Okay, so
Just round it to 14. That'd be close enough.
All right. So,
Uh,
okay. So you said what was what? Okay. Say the formula again. It was something about
468.
468. So I'm going to go, let me see if I can figure this out. No, that didn't work. Go the other way. Um, no, that. Okay, delta. I got to figure out which way, how to do it on the calculator, which where the numbers are plugged. So I do
Okay.
try that again. So it was the 468 divided
Well,
by 13. Yes, so I go 468 divided by 14 into my calculator.
okay.
All right,
Well,
33 delta.
I'm going to cheat because I don't want to use the calculator unless I have to.
Mm-hmm.
So 14 megahertz is the 20-meter band, right?
yes.
Okay.
Okay. So a full wavelength at 20 meters is 20 meters. A half wavelength at the 20-meter band
Another 10.
is 10 meters. 10
Right.
meters is about 10 yards.
10 yards is about 30 feet, so that's your closer number.
Yeah, no. Okay.
What's the approximate length for a half wave dipole cut for 3.55?
All right. So,
Same formula.
468 divided by the 3.5.
and then you go,
Oh, 132. Charlie.
well, I got to figure out how you got that. So it's
468 divided by 3.550.
okay. So I have 131.8. So that's, yeah, 132.
Okay.
That's all
You
I did. Is that right?
you can check it by doing that's the 80-meter band. So it would be 40 meters.
Yeah, I still have to learn all my bands and meters.
So 40 meters is about, 40 yards or about 130 something feet.
Yeah, I'm still like the net. I still have to think about the megahertz to the meter, yeah, band.
Yeah, I'm still learning which frequencies are in what meters and which bands and all that stuff.
But that's a good way to check your answer
Okay.
because sometimes you mess up on the calculator.
Yeah, I do it a couple times and pick the best one.
What is the approximate length for a quarter wave vertical antenna cut for 28.5 megahertz?
All right, so we're going to take.
So remember, quarter wave,
So that's half of the 468.
right?
And so gives you 8 feet. So that's south.
Okay, so I didn't have to do anything with the quarter. I just took my 468 and divided it into my 28.5.
No,
And then you have to divide it by four,
Yeah.
right?
I did the other way. I did 468 divided by 2 because that's what he had said during the lesson, the example in the lesson, and then divided by the 28.5. So I got 8
So
feet.
quarter wave is not something I'm going to plug in. I'm going to use a half rather than a quarter.
Well, that's fine. Do the half and then divide it by 2.
Okay, well, what I did is I took 468, divided 28.5, got a number, and then divided it by
By 2.
2, and
Yeah.
I got 8. So the
Okay.
Okay.
quarter, like I said, the quarter isn't what I'm looking at. We're just going to divide it by 2.
Right.
Okay.
Well, you don't have to remember both formulas.
Okay.
So again, this is the 10-meter band. So we're looking at
So you say. I'm still learning that. I'm still memorizing that.
so a quarter of 10 meters is 2.5 meters, right? 2.5 yards. It's about 8 or 9 feet, right?
All right.
So that's a much better way of doing it because you're not going to have a calculator at your hand all the time. Yep.
Oh yeah, you can use your calculator at, well,
Oh, no, in the class, yeah. But I'm just thinking in real life.
Yeah,
Well, in real life,
you
yeah.
need to get familiar with the meters and frequencies.
yeah,
Mhm.
once I finally get there, I'll be better at it. But right now I'm overwhelmed with all the stuff I'm trying to sink in.
All right.
Okay. So
Okay.